Hello friends, in the previous lecture we looked into how we can handle more than one independent variables that emerge out of a given population. For all our discussion we have been considering a single premise, that is we've been considering a system of n different alloys, and we are measuring the different quantities that are relevant to us as materials engineers. We are measuring these different quantities, and we are trying to rather illustrate these different quantities graphically. Now when we considered a single quantity, which for our discussion was lattice parameter, we discussed, or we presented it in the form of using a scale, and we presented it graphically. Now the ultimate aim of such representation was we wanted to know what would be the probability of a given a new alloy assuming a specific lattice parameter, provided this new alloy is part of that population. So you are working on a specific material system, and you have already worked on some components or some different variants of this particular material systems. So for instance, you are considering a binary system, and you have considered a different combination of this binary system, and to that you are trying to add a new alloy, a new binary alloy with a different composition. Now you wanted to know from the existing data that you have, from the existing analysis that you have performed, you wanted to know what would be the probability of what would be the lattice parameter that this particular alloy, the new alloy that you have developed, would assume. So in order to understand that, we have just been focusing on a single variable that is of interest to us, that is the lattice parameter, and to answer that particular question of what could be the probable lattice parameter assumed by the newly introduced alloy, we initially represented the lattice parameter of the existing population in a scale, and on that scale we rather introduced a bin. We translated that distribution of this population on the scale into an histogram, and we are able to introduce a curve over the histogram, and that gave us the distribution of the population. And this distribution of the population meant that this is how the lattice parameter is rather distributed among the population or among the different alloys that we have considered. Now this distribution we translated it into a function, and this we did so by considering the probabilities, and this function we refer to as the probability density function, and we also were able to introduce the cumulative density function. Now all these probability density function and cumulative density function, so these two different functions, that is probability density function and the cumulative density function, so all these were possible. We were able to estimate it for both these for a specific variable, a specific quantity of the alloy that we have been considering, and this variable, purely from the nature of the quantity, it is rather a continuous variable. So that's the reason why we were able to estimate this probability density and the cumulative density function. Had this variable been a discrete variable, we would have estimated a similar operation could be performed, and that operation would yield us probability mass function and cumulative mass function. So depending on the nature of the variable that we are handling, the terminology associated with it, the terminology that we use to describe the same functions would vary. Now in all these discussions, what we have been considering thus far is we have been focusing on just one independent variable. Now on the same premise, it is also possible for us to consider another independent variable. In addition to this lattice parameter, it is also possible for us to estimate another independent variable. For instance, we have been considering the lattice parameter. It is also possible with respect to the, in addition to the lattice parameter, it is also possible for us to, for instance, measure the density as one other variable, and it is also possible for us to measure the molar volume of all the members of the population that we have accumulated. So what we have is, we have a population of alloys, and for that population of alloys it is possible for us to measure the lattice parameter, density, molar volume, and so on and so forth. For instance, when we considered, when we want an example for a discrete variable, we considered the number of neighbors associated with a given atom in a particular alloy. So that is one of the variable. So it is possible for us to estimate different quantities, and each of these quantities can be categorized into continuous variable and also discrete variables. Now So far, all the discussions that we had, except for the ones in the last session, all the discussion in all these discussion, we considered or we handled each of these variables, or we focused on just one individual variable. Now, in the previous lecture, we combined two different variables that we estimated, that we calculated from the n alloys that we have. Now, again, we have to be absolutely sure about the premise that we are working on. We are not considering one independent variable, and rather we are trying to extract or trying to define or already known dependent variable on it. So we are not trying to establish a relation between a dependent and an independent variable. So there is a dependent variable that is already known to us, and there is an independent variable that we have measured. So we are not trying to establish any sort of quantify the relation between an independent and a dependent variable. What essentially we are trying to understand is, we are trying to understand what could possibly be, or is there any relation between what appears to be or what we know to be two different independent variables. We have no clue, we have no prior knowledge of what we are dealing with here. What is the relation between these two variables or these two quantities that we are measuring? So we have no idea about it. We are just measuring these two quantities. These are new material system that we are working on. So we are estimating two different quantities, and these two, in order to identify if at all there is a relation between these two different quantities, and that is the premise we are working on. So that is the point where we are in, and from that point we want to see, first of all, we want to understand if there is any relation that exists between these two quantities that we have measured, these two variables that we have at hand. It is not that we have already established that there is one independent variable and one dependent variable. Usually when you see a plot, that is x and y plot, often, and in a graph, often we see that the x is assumed to be the independent variable and y is rather the dependent variable, and there we will be able to see a trend. But however, the premise here is quite different. What we have is two independent variables, and we don't have much idea about it. So the data that we have with us is two different data sets, and we want that pertain to two different quantities, and we want to see if there exists any relation between these two independent variables. So that is the starting point of our discussion. When we start off with such a premise, so what essentially then we are able to do is, we are able to rather, like when we handled the individual variables, it is possible for us to represent the distribution of a given population on a scale. Depending on the value assumed by the variable in a given population, it is possible for us to represent that population on a scale. So in this case, we are considering the lattice parameter. So supposing if I have an alloy that is represented by blue, that has the least lattice parameter, it can be represented here. And I have a alloy that has the maximum lattice parameter, it can be represented here, it can be captured here. So we are quantitatively placing each and every alloy on a scale based on their lattice parameter. So one that is assuming green will be here, one that is the one alloy that is represented by gray, that will be here, and one alloy that is represented by blue, that will be here. So this is not nothing new here. We are just representing the population of alloys with varying lattice parameter on a scale. Now we are, in addition to the lattice parameter, we are also measuring, say, density. And when you measure the density, you observe that, or you are just measuring the density, and the density of the alloy represented by blue is the maximum. You observe that the density of the alloy that is represented, so you have a vertical scale, you have a scale that is rather presented as a vertical line, or vertically it is being presented, and based on the values you are assigning or you are positioning your alloy, and the blue alloy, it assumes the maximum density, and the red one, it assumes the least density, and again the green one, the next to blue, when you are going in a descending order, and there is the blue one, and we have our gray, and finally, so we have now represented the different alloys that we have considered, and the densities of these different alloys on a scale that is being vertically presented. Now in both these scales, what essentially we are doing is, we are treating these variables individually, and now since we have created a space by placing these two scales perpendicular to one another, we have created a space. The space allows us to handle both these variables in a pair. Simultaneously, the space that we have created allows us to handle these variables. Now when we do that, then the alloy red and the variables associated with it, that is both the density and the lattice parameter of the alloy red, can be positioned here. So what essentially we are doing is we are either introducing or projecting this variable, the density, onto the space, and also the lattice parameter onto the space, and where these two intersect we are representing that particular variable or that particular, or we are introducing a particular point there, and that essentially shows the way the pair ways if we are treating both these variables as a pair, and it is being represented there. And the same can be extended for the other alloys. So when I consider the ones in green, it will be in this way, and the ones in blue, it will be here, the ones in green, it will be here, and the ones in blue will be here. So what essentially we have done is, instead of handling each of these independent variables individually, now we have handled these variables as a pair. Now, even though there appears to be a trend that exists among these alloys, amongst these variables, it is possible for us to rather describe qualitatively this trend. So instead of handling these two different variables separately using separate scale, now we are handling it together. So in order to have this together, or in order to handle them cumulative or together, or combinedly, what we are doing is we are rather placing those scales that individually handle these variables perpendicular to one another. When you place these scales perpendicular to one another, what essentially you establish is a space, and in that space you are allowed to treat these variables combinedly, and you are allowed to treat these variables together. And when you treat these variables together, there appears in this space, there appears to be a trend that exists between these variables, and this trend can qualitatively be captured by drawing a line. So this trend can qualitatively be captured by drawing a line, and depending on the line, this line can have a positive slope, and here it has a negative slope. So this trend that we observe, this sort of a relation that we observe when we are treating these independent variables together in a space that is brought about by placing these individual scales perpendicular to one another, this is what we refer to as the covariance. So what essentially covariance does is, it first helps us realize if there is any relation between what we assume to be the independent variable. So we started off with this premise. We don't know if there exists any relation between these two variables or these two parameters that we are measuring, these two quantities that we are measuring. We didn't have any clue about it. So once we have gathered that data, once we have gathered that information, when you handle the way we have been discussing about, when it is being handled in this way, that is when it is being handled as a pair in a space that is being created in this manner, then the covariance allows us to see or describe the pattern that we observe. Now, when the straight line that you introduce to describe the covariance, if it is of a negative slope, we refer to it as the negative covariance, and when it is of a positive slope, we refer to it as the positive covariance, as opposed to this relation. If there exists an opposite relation of this trend, if there exists a relation that if I represent it in this manner, for instance, and this relation that is indicated in black can be captured by a line that is indicated in pink. Now the slope of that line would be positive, so that would yield the positive covariance. So there are three possible relations that we could observe: positive, negative, and null covariance or no covariance, zero covariance. When you don't see any such relation, what you observe is a line with zero slope, and that will ultimately give us a zero covariance, a zero relation. Now, if we consider two instances, now we are taking the same approach. We are considering two independent variables, and say for instance L and rho, and these independent variables we are treating it together, and to understand their relations, to see if there exists any relation between these two independent variables. But now we are considering two sets of populations. So we are considering two sets of alloys, N1 alloy, N2 alloy. Let us assume that this is a cerium alloy, this is a cesium alloy. Again, these are new alloys that many people are not interested in, and relatively less people are interested in. So we are working on the cerium and cesium alloys, and there is one N1 population of cerium and the N2 population of cesium. So now the lattice parameter and the density of the N1 alloys are represented by these points here. The ones in black, and the cesium points. So the black is represented by cerium, and the alloys of all these density and the lattice parameter relation is rather the trend that we observe when we combinedly address density and the lattice parameter for cesium. It is in this manner here. So when you consider the relation that exists between the density and the lattice parameter of cerium and the similar relation in cesium, what we observe is in both these cases what you essentially see is a positive covariance. So there is not much change that we observe in both these cases. When you consider qualitatively what is the trend that you see, what is the relationship, in both these cases what we essentially have is a positive covariance. However, in one of these cases the covariance is strong when compared to the other. The deviation is rather less when compared to other. So you have two sets of alloys, and both these sets of alloys, they exhibit positive covariance when you handle their density and lattice parameter. Now what we essentially observe is, even though both these exhibits a positive covariance, the deviation or the strength of this relation, so the deviation with respect to the line that you introduce to dictate or describe the covariance, with respect to this line, the deviation exhibited by the individual alloys are quite different. For in case of cerium there is a significant deviation, but in case of cesium the deviation is not much. So this deviation, based on this deviation, you can state that the cerium has rather a compromised relation. We cannot say bad relation, we cannot say the trend is rather bad, but it's rather compromised. In case of cesium you have a strong relation, or a better way would be to, a consistent way of describing it would be weak. So in case of cerium represented by black cross, the relation, even though there exists a relation, these points, these variables exhibit a positive covariance, there is a relation that is that you observe in cerium with respect to density and lattice parameter. This relation is rather weak. However, in case of cesium, this relation is rather strong, and the way we are able to say this one is weak, or again qualitatively this one is weak and this one is strong, is with respect to the closeness of these points with respect to the line that we have introduced to describe the covariance. So to describe this relation qualitatively, we introduce a line, and by the degree of deviation of these individual point from these lines, we are able to state qualitatively one exhibits a strong relation, the other exhibits a weak relation. In case of cerium the deviation is huge, so what we have is a weak relation. In case of cesium, the one represented by red cross, the points are close to that line that describes the relation, and therefore we state that it has a strong relation. Now when we rather quantify the degree of relation, the way we do it is using what we refer to as the correlation. So the covariance is rather, it helps us qualitatively describe or identify if there exists any relation between the what we assume to be or we deem to be an independent variable. And once we identify that there exists a relation between the two what is deemed to be an independent variable, then when we want to rather quantify the relation, then we go for correlation. When we want to say how much is the trend, so what is the degree of relation, is it a weak relation or it's a strong relation, that can be rather quantified by correlation. The expression for the correlation is rather expressed as, for instance, so we have covariance of x and y, we have seen an expression for it. The correlation of x, when you want to estimate the quantify the relation that exists between the two independent variables, we use correlation, and the expression for it will be the covariance of it divided by the variance of the individual variable. So we are considering, or we are rather taking the ratio of the covariance of the independent variables with respect to the variance, the product of the variance of these independent variables. So the variance are associated with, or they are they pertain to these scales here. So here we estimate the variance of the lattice parameter. So x is the lattice parameter, so the variance of this lattice parameter is rather estimated along the scale. and the variance of the density, that is sigma y square, is estimated along this scale. So they are rather they characterize the population distribution of these alloys with respect to a single independent variable. And we are essentially taking the ratio of the covariance, that is when we are handling these independent variables as a pair, from that we calculate the covariance, and with respect to that we are taking the ratio of the product of the individual variance. So essentially it is similar to that of an operation that we do when we are considering the normalization of a given value. We are essentially rather normalizing a given the covariance, and we are normalizing it with respect to the product of the variance of the individual independent variable, and when we do that we end up with the correlation. Again we are doing this with respect to, so covariance, it includes the variance, or it combines the two variance of, or the variance of these independent variables. It collectively expresses the variance of these independent variables. So it treats these independent variables as a pair, and it collectively represents, and that's the reason why we refer to it as the covariance. Now in case of when we want to quantify the degree of relation that is established by the covariance, the relation we are able to discern it through the covariance, and we want to quantify it, so we use correlation. And essentially what correlation does is it rather normalizes the covariance with respect to the variance of the individual independent variables. And because of this kind of a normalizing act, the correlation value it spans from -1 to 1. The correlation of any two independent variable will span from -1 to 1. So when you have a distribution of points, when you have a data points such that all the data points in this representation, that is we are treating the lattice parameter and the density in a scale, and these scales are rather placed perpendicular to one another, and we are observing its relation, and when we are treating it as a pair and all these points lie on this line, then what we essentially observe is a strong correlation, and in this case the strong correlation. So all these, the line that we use to represent, or use to rather describe qualitatively the relation or the covariance, when on this line all these different points are present, then we have the strongest possible correlation, and that is represented by 1. On the other hand, when the relation itself is inverse, for instance we have our points that are distributed in this way, and these are the points that we observe, and now when you consider the line that we use to describe the relation between the independent variables, and all these points they go through the independent variables, or all these points go on the line that we have considered, it goes through all these points, then essentially what we end up having is again a strong correlation, but in a different direction, or in an inverse, or rather with a line of the negative slope, and that correlation is being quantified, or it is what is indicated by the correlation of -1. So the strongest possible correlation wherein the line that indicates the covariance, and through that line or on that line all the distinct points are present, that is the indication of the strongest possible relation. And these strongest possible relations are expressed either by +1 or -1. So +1 when the line has a positive slope, and the -1 when the line has the negative slope. So we start off with the covariance. The covariance, it helps us understand if there exists any relation between the two independent variables, and for that to express that qualitatively we introduce a line. And now this line helps us, the line that we originally introduced for qualitatively describing the covariance, this line is now helping us in describing the degree of relation. When all the points lie on this line, then it means there is a strong relation, and this strong relation means the value of this correlation is equal to 1. And again, when you have a negative line that is of negative slope, that representing the relation between the two variables, and all these points lie on that negative slope line, then the corresponding correlation will be -1. So there are certain characteristic features associated with the correlation, and this is often referred to as the Pearson correlation. Some terminology that might help you Maybe when you are looking into other correlation techniques which are a bit more sophisticated than the one that we are looking into right now, it will help you to distinguish. So this rather straightforward way of understanding the correlation is what we refer to as the Pearson correlation. Now, having looked into the Pearson correlation, let us consider some of the features or properties of this particular correlation. Now, when we are representing the lattice parameter of a given population, we can represent it using different orders. For instance, we are representing the population of a given or lattice parameter of a given population on the scale, on this axis. Now, it can be expressed, this lattice parameter can be expressed in using or on the scale of 10 to the power minus 10 meter, that is angstrom. It is also possible for us to express it using 10 to the power minus 9 meters, that is nanometer, and it is also possible for us to express it using 10 to the power minus 12 meter. So, a given quantity, in this case lattice parameter, can be expressed on different scales. Now, if I consider expressing the lattice parameter on using angstrom, then let us represent it using, so this would be the distribution of the population. So, we are measuring the alloys in angstrom, and this is the population distribution that we get. Now, the same population we are expressing using nanometer. So, we are expressing the same population using nanometer. Then essentially what we observe is, so when we consider a different scale from that of angstrom, the distribution of the qualitatively the separation of each of these points, even though they would remain the same, but when you consider with respect to the original existing angstrom distribution, it will rather be different. Now, this distribution can be represented on this axis using the green color. So, it will be of this form here. So, put it rather simply, the distribution now is rather shrunk. Now, it is also possible for us to express the same lattice parameter on a different scale, that is a picometer, 10 to the power minus 12 meters. Now, when you consider the representation of the same lattice parameter using a different unit or using a different scale or represented in a different scale, this will now be spread apart. So, this will now be spread apart. So, same quantity, we are representing it in a different scale, and we leave the other quantity that we are considering, that is the density, as it is. So, we leave the density as it is. So, only we are just changing the scales of the lattice parameter. So, same lattice parameter we are representing it on a different scales. And when we do that, so these are the corresponding densities of the 5 alloys that we have considered. So, when you do that, the points that correspond to the representation of lattice parameter using 10 to the power minus 10 meter, that is angstrom, will be of this form. So, when you treat the density and the lattice parameter in the angstrom scale, the relation that you get will be of this form here. So, what essentially you have is, you have a very strong, the strongest possible relation, and the correlation here is equal to 1. So, you have a strongest possible relation when you represent when you consider density and the lattice parameter in 10 to the power minus 10 angstrom, you have a strongest possible correlation that is represented by 1. Now, when you consider the relation between the density and the lattice parameter in the nanometer scale, you get a relation of this sort here. You get a relation of this sort here. So, this relation is also strongest possible because all these points, they lie on the straight line that indicates the covariance. So, similar to that of 10 to the power minus 10 meter scale, even when you consider the nanoscale, you still observe the strongest correlation, that is rather quantified by 1. So, you have moved away from the angstrom scale to that of the nanometer scale, and despite changing the scale of the nanometers, or despite changing the scale in which you express the lattice parameter, you still observe the same degree of relation. And even when you consider the 10 to the power minus 12, the picometer scale, the relation that you would observe will be of this form here. So the relation that you would observe, so the points that we would be looking into can be expressed like this. So the points that we will be looking into will be like this. And when we have such a point, even then the correlation or the line that describes the covariance will pass through these individual points again, and it exhibits the strongest possible relation. So what essentially we observe is the correlation is rather scale invariant. So this correlation is rather scale invariant. So when you observe a strongest possible relation on a specific scale, even when you change the scale, the degree of the relation still remains the same. So this is what we are saying by considering this simple example. So we have seen that what we have observed is, we have observed that on the angstrom scale, when you compare density or when you relate density and the lattice parameter, you see a strong correlation. Now when you change the scale of the lattice parameter from angstrom to nanometers, even the strongest possible relations still remains the same. When you again shift it from the nanometer to that of the picometer, the strongest possible relation still remains the same. So this strongest possible relation, the degree of relation which is expressed by the correlation, it remains unchanged even when we are changing the scales. So what we observe is the correlation is rather a scale invariant. One other critical property of, or one other critical feature that we need to consider while we are discussing the correlation between two variables x and y is that this correlation, we are quantifying this correlation, the way we are graphically understanding the degree of relation and what should be the value of the correlation is when the line that speaks of or that describes the covariance, when the points are present on these lines, then we say that the relation is the strongest and it has the maximum correlation. So that is the way we are describing or quantifying the relation. It depends on how much shifted are our points from the line that describes the covariance. When the points lie on that line, we state that it is the strongest possible correlation or is the strongest possible relation. So in all these three cases that we have seen, all these lines lie on all these points lie on the line that describes the covariance. So therefore we have stated that these are the strongest possible correlation, and therefore we have assigned the value of 1. Now supposing if I have just 2 points, say 1 and 2, now these 2 points can rather be connected by any straight line. So these 2 points, when I connect these 2 points, it is possible for me to connect these 2 points using a straight line, and this straight line essentially is what dictates or it was describes the covariance. So essentially when I have just 2 points, always the relation that exists between, or always the relation that exists in these when I just have 2 data points is 1. But this relation is not because of, or this value of the correlation is not because of the relation, but it is because of the number of data points that I have. Because I have only just 2 data points, the only relation or only correlation that is possible for me to have is 1. Because the correlation, the way we have defining the correlation is based on how much away from the line that describes the covariance is. So when we consider several points, and depending on how far away these points are from these lines, so based on that we define our correlation. But when I have just 2 points, the line I draw will be between these 2 points. The line I draw will connect these 2 points. So these 2 points will always have to lie on this line. So all that I have is, all that I have considered is just 2 alloys, and I have measured the lattice parameter and the density of these 2 alloys. If that is the case, then if I want to find the relation between these 2, then always I will end up with a correlation of that will be equal to 1, that apparently shows that exists the strongest possible relation between these 2 independent variables. However, the problem is, because we have just 2 alloys, or because we have just 2 points or 2 data points, because of this restriction, the correlation we observe is rather equal to 1. It is not the reflection of its relation, it is a reflection of the number of data points that we have. So therefore, the accuracy of this correlation needs to be dependent on we have to make the correlation makes sense only in relation to when we view it along with or in consideration with the number of data points that are present. So whenever we just have two data points, it doesn't really make any sense, because all the time it is what we observe often, or the only possible way of having a line, of describing a line that rather indicates the covariance must go through these 2 points. So therefore, the only possible correlation is equal to 1. The correlation makes sense only with relation to the number of data points that we have. Now in this case, the correlation doesn't give any significance. The correlation will be of absolutely no significance here, because all these two data points will lie on a line that connects these two. So therefore, ultimately you will end up with a correlation of 1, and it absolutely makes no sense. Now on the other hand, if instead of these 2 points, if say we have 3 different points, it is not easy for us to have a straight line that goes through all these 3 different points. So therefore, some degree of understanding about the correlation can be gained from these 3 points. So if we had just 2 points, the only line that we could draw will go through those 2 points. So that means it will not have much significance. The discussion on the correlation will be not of much significance. On the other hand, if we have 3 points, it does not require, or a single line, depending on the way these 3 points are distributed, right? It does not have to be that the single line should include all these 3 points, like in case of the 2-point condition. So therefore, in the case of a data set with 3 points, the correlation makes more sense than the data set with just 2 points. So the significance of correlation, it is dependent on the number of data points that we have. Now the other way of putting it would be, in this case of 2 points, wherever these points are positioned, so these 2 points, now we have considered these positions, these points can be positioned like this as well. So these points can be this as well. So irrespective of their position, their correlation is going to be 1. However, when you consider these 3 points can be this, these 3 points can be this. So depending on the distribution of these points, their correlation would vary. Sometimes they may have a good correlation, sometimes they may have, even though the signs here may not be different, but sometimes they may have, their closeness will be, they might be much closer, or sometimes they may be further apart. So the degree of relation would vary. So therefore, when you talk in terms of probability, when you just have 2 points, the probability of having the correlation equal to 1 is 100%. So it's 1. So the probability when you just have 2 points and having a specific correlation, so that specific correlation is 1 here, to have the specific correlation is 1. So irrespective of what these positions of these 2 points are, irrespective of what the relation between the lattice parameter and the density is, what type of relation that we have, when you have just 2 quantities, when you just have 2 data points, then essentially the correlation that you end up with, which is 1, will happen. So the probability will remain the same. It will not be dependent on the relation that exists between these variables. So irrespective of the nature or the positions of this point, the probability of achieving the same correlation is 1. So when you just have 1, when the number of when the population size is just 2, the population size is just 2, the probability of achieving the correlation of the population which is size 2 is equal to 1. So this population can be distributed in any way possible, but the correlation of it is going to remain the same, which will be equal to 1. So when you have 2 data points alone, and from that 2 data points you get a correlation, the same correlation you could get with any 2 data points. So the probability of getting a specific correlation with a given set of points is going to be the same, and it is going to be 1. So the given data points is 2, and with that 2 data points you are getting a specific correlation. you will get the same correlation for any combination of such two data points. So that is equal to 1, and that is what we refer to as the p-value. So what p-value, when you observe this term p-value, what it helps us understand is how much significant is your correlation. Now when your p-value is 1, when your p-value is maximum, what it means is the data point that you have will have, so when you consider similar such a population of data points, and the correlation, that the value that you have gained from these two data points can be gained from other such combinations as well. So in the initial case, we have considered just two data points. It is possible for us to have several such data points or several such combination of data points. So we have here one combination, we have here another combination, and we have here another combination. So all these combinations give us the same correlation value. When there are several such combinations that will give us the same correlation value, what it essentially means is that the probability of having the same correlation is huge. So that means the p-value will also be huge. However, when you increase the number of data points, the correlation assumed by this particular combination of 3 points will be much different from this particular combination of 3 points. So in order to have the correlation that is associated with these combination of 3 points, we have not much options. So the probability of another set of 3 points having the same correlation value is much reduced. So the p-value in that case will be reduced. So what p-value essentially states is, the p-value states if I have a given set of points and if I reconfigure it, and if I am able to arrive at the same correlation that originally exists, so it means I have a probability, an increased probability of arriving at the same correlation. So the p-value will be higher. So the p-value will be lower when it is rather not possible for us to have this characteristic correlation value for a given distribution of the data points. So in this case, in the case of two data points, there is no characteristic correlation because all the two data points will yield you the correlation of 1. But in case when you increase the number of data points to 3, it is possible for us to have, it becomes rather difficult for us to recreate the similar correlation, to arrive at the similar correlation with different position of these data points. So that means the probability of arriving at the same correlation, with different positions of the existing number of data points is less. So when the p-value is less, the significance of the correlation increases. So what essentially we are capturing is, so one of the characteristic feature of the correlation is the significance of it depends on the number of points, the population of the data set. When you have just two data points in a given population, it is always the correlation will be equal to 1. However, it is possible for any configuration of these two data points to assume this, or to have the correlation of which is equal to 1. To have the same correlation, we can have different configuration of this two data point. So that means it is highly probable for us to have any two data points with the same correlation. On the other hand, if we increase the number of data points, it becomes difficult. The probability of having the same number of data points but in a different position, but to ultimately render us the same correlation is not much probable at all. So then this probability will decrease, and this is what we refer to as the p-value. So as your number of data point increases, arriving at the same correlation by changing their position is the probability of arriving at the same correlation by changing the position becomes difficult. So this probability is being quantified by the p-value. When the p-value is low, then the significance of the correlation is higher. So p-value essentially it quantifies the probability of arriving at the same correlation that relates the set of points by changing its position. Now in case of 2 points, irrespective of how you change the position, the probability you will ultimately arrive at the correlation 1. So therefore the probability is maximum. On the other hand, if you have a population of 3 data points, it is not that easy to change the position and arrive at the same correlation. So in that case, the p-value will be lower. When the p-value will lower, the significance of the correlation is higher. So what we have seen is, so far we have looked into more update from the qualitative description of the relation that exists between two independent variables. We have attempted to quantify this relation. We have initially described it as strong and weak relation, and now we are able to express the strong and weak relation using a specific value between -1 and +1. And the way to calculate the correlation, we have seen the formula that is being used. Now we have seen the features that are associated with the correlation. One is it is a scale invariant, and finally we have seen that depending on the number of population or the number of members that constitute a population, the significance of the correlation would vary, and essentially it is through the p-value. So this p-value is essentially, it captures the significance, it indicates the significance of the correlation. When the p-value is lowest, it will help us rather understand the significance of the correlation. With this, we will wind the lecture up, and we will, if possible, we will look into one other component of the relation that exists between the different parameters in the subsequent lectures. Goodbye.